Okay, bond electronegativity difference. So this should be the title at the top of your notes. So we've talked about electronegativity. Copy down those notes as a refresher. Okay, so what do we mean by electronegativity difference? We know what electronegativity is. We know that the values are listed on table S, right? So you could go look those up. I also put a little chart here for you for easy reference. So difference, right? Difference when we're talking about math is when you subtract two things, right? The answer to a subtraction problem. So we're going to be subtracting electronegativity differences between the two atoms bonded together. So let's try some. All right, so we'll start with H2. That's two hydrogens bonded together. And the electronegativity is 2.2. I'm going to subtract 2.2 because that is the other atom that's in the bond, and that's going to give me 0. All right, so let's try something else. Let's do HCl, right? So that is a hydrogen bonded to a chlorine. Like we said, hydrogen's 2.2. I'm going to subtract the electronegativity value for chlorine, and that's going to give me 0.96. Okay, and let's do one more, just for fun. Do sodium chloride. All right, so that's a sodium bonded to a chlorine, and that's going to give us 0.90, that is sodium. Subtract the electronegativity value for chlorine, and that will give us 2.26. All right, so you might ask yourself, who cares? What do these numbers mean? Why are we doing this? All right, so the difference in electronegativity will tell us what kind of bond there is. All right, so let's go back here, and we'll start with sodium chloride. So sodium chloride is 2.26, and that is going to be greater than 1.18. So 2.96, that is above 1.8, greater than 1.8. And bonds that have a electronegativity difference above 1.8 are ionic compounds. Ionic. Okay, so if we go back here, right, we can definitely see that sodium chloride is ionic, right? We have a metal and we have a non-metal. Okay, so now what about HCl, right? That's 0.96. 0.96, we can see that that falls between 0.4 and 1.8. Alright, so that's going to go right in the middle there. And we call these kinds of bonds polar covalent. Okay, what does polar mean? We'll get to that in a second. So these are called polar covalent bonds. Right, and lastly, we have our, so that was our polar covalent, and here we have 0. Let's go back over here. This is less than 0.4, right? So that is going to be what we call non-polar covalent. And we will talk about this whole polar, non-polar thing in 1 second. Polar, non-polar, non-polar covalent. All right, polar, non-polar, what does that mean, right? We already know what ionic is. So let's look at this whole polar, non-polar thing. All right, so polar and non-polar, let's take a look at H2 first, right? If we take a look at this picture, we can see that the electrons are right in between the two hydrogens, right? They're sharing them nice and equally. They're happy. There's no difference in the electronegativity. Now let's go over to HCl, right? That is the one that we determined was a polar covalent bond. So we know that when we go over to the right-hand side of the table, the elements start getting more electronegative, right? And more electronegative means they are pulling harder on the electrons. So if you take a look at this picture, right, hydrogen looks kind of stressed out, chlorine looks like a, evil, crazy person, and we can see that the electrons are no longer in between being shared equally, they're over here, right? Chlorine is pulling on the electrons harder. So when we have these bonds, right, sometimes one of the elements is pulling harder on the electrons. And what happens then is that the electrons are on that side now, right? And we remember the charge of an electron is negative, right? So in this situation, the electrons are being pulled towards chlorine, okay? So to show this negativity on that side, we draw this little arrow, right? So the arrow is pointing towards the more electronegative element. And to show that this side is negative and the other side is positive, we use this lowercase delta, this Greek letter, all right? And that's going to have a negative sign. This one is going to have the same thing, but a positive sign. So that is how we write the notation for that, these little gammas. Delta, excuse me, lowercase delta. Okay, so let's do some practice. All right, I have sodium and chlorine. So what we're going to do is we are going to find our electronegativity values and we are going to subtract them. And you are going to try these on your own before I give you the answers. So let's see. Try this one out. Sodium chloride. Okay, and that is going to be an ionic bond. We already knew that because we did that as an example already. Whoops. And we can already see, right, before we even do the math, that's an ionic compound. All right, so let's try the next one. All right, 0.41, so that would make it... All right, so I know we said the cutoff was 0.4, but 0.41 is pretty darn close, so we will consider it nonpolar covalent. Okay. Carbon, carbon. Right, so this is just like our hydrogen example. If it's two of the same bonded together, then the difference is going to be 0, and that will be nonpolar covalent. All right, hydrogen and oxygen. Okay, 1.24, which would make it polar covalent, right? Because that is above 0.4. Fluorine, fluorine. Okay, again, that's going to give us 0, which would make it okay, and last but not least, potassium and oxygen. Okay, and right from the start, right before we even did any calculations, we remember that potassium is a metal, oxygen is a nonmetal, so that will be an ionic bond. All right, so we will practice this more tomorrow in class, and you let me know if you have any questions.